we have seen that the action of the rotation operator on an angular momentum eigenstate gives rise to a linear combination of angular momentum eigenstates again, but this time with the same eigenvalue for j square but different corresponding eigenvalues for jz. So this was our relationship. And the matrices formed by the elements dj m prime m contain all the information that is necessary to understand rotations or the action of rotations on kets. So an important question at this stage could be, how do we determine these matrices? Of course, determining these matrices means that you have to determine the matrix elements, namely the numbers dj m prime m corresponding to n hat theta rotation. Now, since the eigenvectors j comma m prime are mutually orthogonal and normalized, it is easy to see that there is one very easy way of figuring out what this coefficient here is going to be. All you have to do is take the full vector, which is this, and sandwich it with the bra corresponding to j m prime. So the result is simply this. So the matrix element dj m prime m n theta is nothing but the matrix element between the states between the bra j m prime and the ket j m of the rotation operator u n theta. So this is essentially how we are going to calculate these matrix elements. But before we go on to talk about calculating matrix elements for rotations, let us remind you of something which you must have studied in your classical mechanics course about one very important way of representing rotations. Maybe you have already guessed what I mean. I am talking of the Euler angles as a means of representing rotations. Of course, on the left here you can see a picture of Leonhard Euler, the grand old man of mathematics, who did, well, you name it, he did it. Introduced the Euler constant, which we know as simply E, dappled with complex numbers, worked out infinite sums, and did lots and lots of things besides. He also taught us a way of representing rotations, an arbitrary rotation, which takes you from a coordinate frame xyz to another frame capital X, capital Y, capital Z, in 3 steps involving 3 individual rotations. So let me just try to show you the picture of this thing in close-up. So here you have the original frame, the original x-axis, y-axis, and z or z-axis, which is vertical here. This was your original coordinate frame, and when you rotate your coordinate system, the frame ultimately becomes capital X, capital Y, and capital Z. So how did Euler go about doing this? He broke this rotation up into 3 steps. First, he rotated about the original z-axis through an angle alpha, so that the x-axis came here to x prime, the y-axis moved here to y prime, and of course the z-axis stayed where it was, z prime. Now the reason for doing this is essentially to set up the y-axis so that now I can rotate about the z-axis, about the y-axis, the new y-axis, y prime axis, so that I can actually end up with the z-axis moving to the correct final position. That is, once I rotate through an angle beta about the y prime axis, the z-axis moves, z-axis which was the same as the z prime axis, after all it did not rotate in the first step, is now moved to this new position z double prime, which is the same as capital Z. Of course, in the process, y prime axis stays unchanged, so y double prime is the same as y prime. The x prime axis, of course, moves to x double prime here, so it goes down to an angle beta. Finally, you have to you have got the, notice that at this stage you have got the z-axis in the right place. What that also means is that the current x and y axis, that is x double prime and y double prime, are in the correct plane, although not yet in the correct position. To move them to the correct position, all you have to do is rotate about the z-axis or z double prime axis through an angle gamma, which moves the x double prime and moves it right to capital X. And of course, that also ensures the y double prime will move to capital Y. Just to remind you of all this again, let me just show you this in steps. So this is the initial scenario. You have x, y, z, all three axes. The original small x axis is this one. This is small y, and the one vertical is small z. And now we are going to first carry out a rotation about the small z axis, so that we turn the small x axis into a new one and the small y axis into y prime. So here goes. A rotation through an angle alpha about the z axis moves you here. Now once again, let me stress, the reason why I have done this is that y prime now is in a position, it's actually perpendicular to the plane formed by z and the final capital Z. So that now if you rotate about y prime through an angle beta, you can move the z axis to the right position, and this is what we have done here. So we have rotated about the y prime axis, that is why y double prime stays the same as y prime, and here you have a rotation of beta. So now z is in the right position, which means capital X, small x and small y, which are now x double prime and y double prime, are in the correct plane. So all I have to do is rotate about the capital Z axis, the double prime axis, which is the same as the capital Z axis, through an angle gamma, so that I can move all the three coordinate axes to the right position. So that's all Euler angles are. Now, if you remember what you studied in your classical mechanics course, you may be feeling slightly confused, because in classical mechanics, almost certainly what you were taught is that the first rotation is going to be about the z-axis, as here. The second one is going to be about the new x-axis, x prime, and the third one is going to be about the new z-axis. So there you may have studied a sequence of rotations: original z-axis, new x-axis, newer z-axis. Here we are studying a sequence, or we are using a sequence: original z, new y, new z. Now the reason for this is sort of conventional. In quantum mechanics, we almost invariably use this z, y, z convention for Euler angles, rather than the ZXZ convention, which classical mechanics mostly uses. And you will soon see, when we begin talking about matrix elements, why is it that we talked about we are using this ZYZ convention for Euler angles. But now, enough pictures, let's go back to the maths. So this rotation R, corresponding to the Euler angles alpha, beta and gamma, which we denote as R alpha, beta, gamma, let me remind you, this is formed by a succession of three rotations. First, a rotation about the original Z axis to an angle alpha, corresponding to the matrix RZ alpha. Then we rotate about the new Y prime axis through an angle beta, RY prime beta. And finally, we rotate through the newer Z double prime axis, which is the same, remember, as the Z axis, through an angle gamma to get RZ double prime gamma. So finally, if we string them all together, we get R alpha beta gamma is R Z double dash gamma, R Y dash gamma beta, RZ alpha. Remember once again, that's the matrix on the right acts first. So this is the first rotation, then we have the second rotation, and finally we have this third rotation. Now all this is fine, but there is only one catch here. Here the three rotations are about three different axes, and these axes are not, apart from the very first one, these are not the original coordinate axis. So of course I can write down rotation matrices for arbitrary axis, but given the fact that I know what Jx, Jy, Jz matrix elements are going to be, it is going to be much neater if we could write everything in terms of rotations about the original axis, the x, y or z axis, whatever we need. It turns out that there is an easy way of doing that, but for that, to understand that, we first need to make a detour. Well, this detour is about how to connect rotations. The title is, the heading here is slightly wrong. It's not rotations about an arbitrary axis really. It's more about how to connect rotations through the same angle about two different axes. So let us consider rotation R0 that can carry an axis n prime to an axis n. Now, is R0 unique? The answer of course is no. If you find one rotation R0 which works, I'm pretty sure you can figure out infinitely many more rotations that will do. For example, you could first start with a rotation, some rotation about the n hat prime axis, which will not change n hat prime at all, then carry out R0, which will move the n hat prime to n, and then, why stop there? Then finish off by some other arbitrary rotation about n hat. That will have exactly the same effect. So this R0 is not unique at all. All we need here is some rotation R0 which carries the n hat prime axis to the axis n hat. Now the question is, can we relate, or the statement here is we can relate a rotation about the axis n hat, which is a new axis, through an angle theta, namely r n hat theta, to a rotation through the same angle theta about n hat prime. And how do we do this? Well, we do this in 3 steps. We first carry out r naught inverse, which moves n hat back to the n hat prime axis. Remember, r naught moved n hat prime to n hat, r naught inverse moves n hat back to n hat prime. Then we rotate about n hat prime through an angle theta, which is presumably a rotation which we already know. It could be that n hat prime is some simple axis like x or y or z. Doesn't have to be, but could be. And then rotate the n prime axis back to n. So this is the prescription. Rotation about n hat theta of r n hat theta is r naught, r n hat prime theta, r naught inverse. Once again, remember, r naught inverse gets to act first, then r n hat prime theta, then r naught. Of course, at the level of corresponding quantum operators, we get the result u n hat theta, the operator which describes what happens to kets when you apply a rotation of coordinates through an angle theta about the n hat axis, is given by u naught, u n hat prime theta, u naught inverse. Of course, u naught here is the operator corresponding to the rotation of coordinates r naught. Now, with this aside out of the way, let us go back to the question of Euler angles. Remember, we had so far figured out that the Euler, for the rotation corresponding to alpha, beta and gamma Euler angles is rz double prime gamma, ry prime beta, rz alpha, and the only problem with this expression so far was that all the 3 rotations are with respect to different sets of axes. Only one of them, the first one, rz alpha, is actually with respect to the original set. The others are with respect to new axes, which you obtain by carrying out rotations. Now, it's easy to see that the z double prime axis could be obtained from the z axis by a successive operation of rz alpha followed by ry prime beta. Right? So, ry prime beta rz alpha carries z to z double prime. Now, from the rule that we had just figured out, it says that the rotation about z double prime through the angle gamma is related to the rotation through the original z axis, about the original z axis through the angle gamma, by this particular transformation. Now, the great thing about this is that if you notice in our expression for R alpha beta gamma, you have RZ double prime gamma followed by a pair of operators which is exactly the inverse of what is sitting here. What that means is our expression for R alpha beta gamma considerably simplifies. You just have this pair of matrices followed by RZ gamma, and that's it, because whatever came after that in RZ double prime gamma cancelled with what you have in R alpha beta gamma, which is this. Now this is a lot better in the sense that we have two successive rotations through angles alpha and gamma about the original z axis, but there's still this rotation about the new y axis here. But remember, the way in which you obtain the y prime axis from the y axis is by applying Rz alpha. So Ry prime beta must be Rz alpha, Ry beta, which was the original y axis, Rz inverse alpha. And if we take this and plug it back into the original expression, we end up with this result. R alpha beta gamma, the overall rotation through Euler angles alpha, beta and gamma, is rather surprisingly given by Rz alpha, Ry beta, Rz gamma. What is surprising about this result is, although in the actual description of Euler angles we had rotations about the z-axis first, then the new y-axis, then the new z-axis, here all the three rotations are with respect to the original axis. But notice that they are through the same angles alpha, beta and gamma, but the order has been reversed. It's the Rz gamma rotation which has to be done first, then the Ry beta rotation, then the Rz alpha rotation. So same rotations, but about the original axis now, same angles, but the original axis and in the reverse order. So what does this tell me about the corresponding rotation operators? Now that we have this result that R alpha beta gamma is Rz alpha, Ry beta, Rz gamma, we simply can write down the corresponding rotation operators acting on the kets in this form. The rotation operator corresponding to U alpha beta gamma must be Uz alpha, Uy beta, Uz gamma. That is, in this case, Rz gamma acts first and Uz gamma acts first on the corresponding ket. Then Ry beta acts next on coordinates, Uy beta acts on the ket. Rz alpha acts on coordinates, Uz alpha acts on kets. And since we know what these individual rotation operators are, that exponentials of I times the angle by h cross times the generator component or the angular momentum component in that direction, we easily get this result. U alpha beta gamma is e to the I by h cross alpha jz times e to the I by h cross beta jy times e to the I by h cross gamma jz. And finally, we are in a position to write down the matrix elements that we were looking for. All we have to do is sandwich this operator e to the I by h cross alpha jz plus into whatever, all this product in between the bra j m prime and the ket jm, and that will give us dj m prime m corresponding to the rotations or corresponding to the rotation given by the Euler angles alpha, beta and gamma. Now this expression is actually quite easy to calculate, at least in part, given the fact that jz eigenvectors are sitting here in this expression, e to the I by h cross gamma jz acting on jm and e to the I by h cross alpha jz acting on the bra jm prime are both pretty easy to calculate, and so we finally end up with this result. These two jz factors, exponential jz operators, gives you this exponential term, and the rest of the factors, small d j m prime m beta, depends only on one angle beta, and this is simply nothing but the matrix element between Jm prime and Jm of the exponential of I by h cross beta Jy. Now, notice that in our convention that we have used so far, J plus and J minus have purely real matrix elements, which actually means that Jy will have purely imaginary matrix elements, which means that the operator which is being exponentiated here, which has I times angle beta by h cross times Jy, this is a purely real matrix. And this ensures that the small dj m prime and beta are purely real numbers. Now this actually is the reason why quantum mechanics people prefer to use a ZYZ convention for Euler angles. Had we used ZXZ, nothing much would have gone wrong, but here you would have to actually figure out matrix element between Jm prime and Jm of a rotation about Jx, and Jx matrix elements being purely real. This would have been an exponential of a purely imaginary matrix which would have complex elements in general. So the only reason why in quantum mechanics we use a ZYZ convention for Euler angles is to ensure that apart from these simple pure phases, the rest of the matrix elements are all purely real.